We're given here one of our first examples of a vector function in space. Just the vector equation of kind of the most boring helix we can have. Now our helix now, instead of being between 0 and 2 pi, all I know about time is that it goes on from 0 forever. So now we have a helix that's going around the z-axis forever, right? It's infinitely tall, and we're asked to find the unit tangent vector, the principal unit normal vector, and something else that's being obscured by a box with a bunch of question marks on it. Hopefully that's exciting and what the video is actually about. But to start, let's just see if we can draw a picture of this vector valued function, this helix, and then calculate t and n. So I want to be in a right-handed coordinate system. And we've looked at this helix before. And I know it's above the xy plane because t is bigger than or equal 0, which means the z-coordinate is bigger than or equal to 0. And if I just think about plugging in 0 for t, I know I'll start at this point, and I spiral around the z-axis. Between 0 and 2 pi, I make one full revolution. So I end up right above that point when z is equal to 2 pi, and we would just keep spiraling around this time. And we'll pretend that this is a good helix. Where I am imagining a slinky that's been stretched out there from the xy plane. All right, we're asked to calculate big T and big N. I need a velocity vector. All right, now I need to know speed. Well, we've done this for this particular graph before. Sine squared plus cosine squared is 1 plus 1 more is 2, so the speed is the square root of 2. This lets me calculate big T. I know some of you watching this video are mad that I'm not rationalizing my denominators. Well, I know that's root 2 over 2, and that's all I need to know. I'm happy with that 1 over root 2. All right, so I found big T. Now I need to find big N, which means I need to take a derivative. I need to find dt dt. Minus 1 over root 2 cosine t minus 1 over root 2 sine t comma 0, and then the magnitude of that vector. Well, let's see. This squared plus this squared, well, that's going to be 1/2 cosine squared plus 1/2 sine squared would give me 1/2. That's a 0. So the magnitude of that vector is just 1 over root 2. You could actually observe that by just factoring out a 1 over root 2 and noticing that you have cosine and sine sitting in there, and that's a unit vector. All right, so I can calculate big N. Minus cosine t, comma minus sine t. Comma 0 fell off the board. All right. So I know big T, I know big N. Let's actually think about big T and big N for a particular value of t on this helix. Let's let t equal pi halves. I want to find big T at pi halves and big N. All right, so big T at pi halves. All right, well, let's think about it. The sine of pi halves is 1. The cosine of pi halves is 0. And the z-coordinate here is always 1. Okay, and now big N at pi halves. All right, so big N sitting over here. Now I have cosine of pi halves. Well, that's 0. Comma. Minus sine of pi halves. That's going to be a minus 1, and that's going to be a 0. So I have big T and I have big N. Thinking about this helix. Now, just think big T and big N are supposed to be normal to each other. Look at the dot product. they zero out, right? 0 plus 0 plus 0, right? They're not always that nice, but they do always equal 0 if you dot product those two things. All right, so let's think about that helix. I know I haven't graphed on the other board, but I just want to think about up to that point at pi halves. So I start on the x-axis and I spiral around until I'm just over the y-axis, and my curve would keep going. So let's think about r of pi halves, right? That point sitting right there. Well, that's what the original function would give me. So cosine of pi halves, that's 0. I have sine of pi halves, which is 1. And then the z-coordinate is just t, right? So I'm sitting at that point right there. T is describing the direction of motion. So I start at this point, right? And in the x direction, I go backwards, minus 1/2. In the y direction, I do nothing. In the z direction, I go up 1 unit. So I've gone backwards on the x-axis and up 1 unit. The direction of motion would look like that. Probably not drawn to scale. Okay, now look at the normal vector, and let's imagine drawing it from that point. I do nothing in the x direction, I do nothing in the z direction, but in the y direction I go in the negative direction 1 unit. So there's big N. So if I think about that, at that point, I have a direction of motion going this way and a normal vector saying, hey, my helix is curving that way. And okay, well, tangent normal, that's a good 2D kind of description of what this vector is doing at that moment in time. But this curve's moving through 3 space, and we've described at this moment that we're kind of going that direction and turning in that way. But it seems like there should be a third thing, right? If I have t and n, it seems like there should be this third vector perpendicular to both of them, and there is. And we call that vector b. It's called the binormal vector. It's a really creative name. Not really. It's normal to 2 things, t and n. We call it the binormal vector. Together with t and n, they kind of give every point their own 3D coordinate system. Direction of motion, principal unit normal vector, and then a mutually orthogonal vector b. We want the binormal vector to follow a right-hand rule from t to n, so I bet you already know how to calculate it. The binormal vector denoted by a capital B with a vector hat is the cross product of t and n. So let's find b of pi halves for our previous example. To find b of pi halves, I just simply need to plug in t and n, and since I've already evaluated those vectors at pi halves, I can just plug those quantities in. I could also be asked to find the binormal vector as a function on time, right? Plugging in actual components from t and n. That can be a little more challenging of a calculation. So watch for instructions. If you're asked for t and b at one moment in time, evaluate t and n at that moment, and then just take the cross product of two constant vectors. All right, so the I component, well, 0 minus a minus 1, that's going to be I. The j component, 0 and 0. And then the k component, I get plus 1 over root 2k. And there's my binormal vector, except for I've clearly made a mistake because this isn't a unit vector. And the binormal vector is guaranteed to be a unit vector, right? Because the definition tells me that the magnitude of b is the magnitude of t times the magnitude of n times sine of the angle between t and n. Well, The angle between t and n is pi halves, so sine of pi halves is 1. These are unit vectors. 1 times 1 times 1 is 1. So I've made a mistake, and I'd like to find that mistake. And I think I know where it is. When I wrote down t, I copied it down wrong. Right? I wrote a 1 here, and it should have been a 1 over root 2. And I've kind of accidentally erased some of these things. All right, well, let's make sure t still points in the right direction that I drew down here. It goes back in the x direction, minus 1/2, and then up 1 over root 2. Okay, so that actually probably makes it a little more to scale than what I had. And I should really reshoot this video, but I'm going to leave it like this. Because, well, I'm human. We've made it 11 minutes into a video, and honestly, I think it's a good thing to see that we have to think through all of these things. That I got something at the end that couldn't possibly have been the binormal vector because it wasn't a unit vector. And now it is, right? If I try to take the magnitude here, I'll get 1/2 plus 1/2 is 1, the square root of which is 1. So I feel much better now. By definition, the binormal vector is a unit vector that's perpendicular to both t and n. And hopefully we'll do another example.